So is it visible?
Yes. Yes. Right.
Okay.
So
Shall I?
wait, I'll just introduce you and then you can start.
Okay, okay, sir.
Okay. So for the last young scholar talk of the day, I'm happy to introduce Ashima from the Himachal Pradesh University of Shimla, and she will talk about recursive construction of normal polynomials over finite fields. Over to you, Ashima.
Thank you, sir. Uh, Good evening, everyone. This is Ashima. I am pursuing my PhD under the supervision of Professor P.L. Sharma in Himachal Pradesh University, Shimla. The topic of my presentation is recursive construction of normal polynomials over finite fields. Some results regarding construction of irreducible polynomials as well as for normal polynomials over finite field having characteristic P are already given in the literature using some certain transformation. Here we use the transformation this x raised to power p minus x raised to power p minus 1 plus 1 upon x raised to power p to construct an infinite sequence of irreducible polynomials starting from an appropriate initial irreducible polynomial. Then further we show that these polynomials are also normal polynomial of degree NPR. Some introduction about this work. The construction of high degree irreducible polynomials and normal polynomials over finite fields have attracted the attention of several authors. The construction of normal polynomials and irreducible polynomials are already there in the literature by using some suitable transformation. Then we thought about this transformation to prove to construct irreducible polynomials, and then using the same transformation we prove that these polynomials are normal polynomials. For the definition of normal element, an element alpha is said to be normal element if the elements alpha, alpha raised to power q, so on up to alpha q raised to power n minus 1 are linearly independent over fq. And a polynomial, let me say px is it if we have an irreducible polynomial px, then we say that this polynomial is normal polynomial if any of its root is normal in its extension. Alizada et al. Constructed the sequence of self-reciprocal normal polynomials over finite field having even characteristic. Then we extend this construction for finite field having characteristic P, and a family of normal polynomials of degree 2 raised to power is already given by Gao. Then we construct the sequence of irreducible polynomials by taking a suitable chosen initial irreducible polynomial, and then we prove that these polynomials are normal polynomials. These are some preliminary results which are helpful in the subsequent section. Uh, the definition of trace function for any element alpha belongs to fqn. The trace function, which is denoted by trace of qn by q, where qn is the fqn, it is basically fqn, which is an extension of fq, and the trace of alpha is defined by trace of alpha, which is sum of elements of normal basis, that is alpha plus alpha raised to power q, so on up to alpha raised to power q raised to power n minus 1. Then next is the definition of reciprocal polynomial. If we have a polynomial f of x, then we say, and then it's reciprocal polynomial, which is denoted by f star x and is defined by x raised to power n f of 1 by x. The next result is, these results we will use in the further section. If we have two polynomials f of x and gx, which are relatively prime polynomials, and a polynomial px be an irreducible polynomial of degree n, then the composition f of x is equals to g raised to power nx p of f of x upon gx is irreducible over fq if and only if f of x minus alpha of g of x is irreducible over fqn, where alpha is a root of the polynomial px. Then next result is, if we have an element a of fq and p with the characteristic of fq, then the trinomial x raised to power p minus x minus a is irreducible if and only if trace of this element a is non-zero. These are some notations which we'll use in next section. If we write n is equals to n1 p raised to power e with GCD of n1 and p is 1, and we denote pe by t, and the polynomial x raised to power n minus 1 has the following factorization. And these polynomials var phi x into var phi 2x so on up to var phi kx, these are distinct irreducible factors of the polynomial x raised to power n1 minus 1. Then we write phi ix by write it as summation of tiv into x raised to power v, where mi is n minus degree of this var phi x. Next, the following results are helpful to determine whether the irreducible polynomial is normal or not. If we have a polynomial f of x, which is irreducible polynomial of degree n, and alpha be a root of it, then we suppose that x raised to power n minus 1 factors as in 1 and phi ix be as in 2, then the polynomial f of x is the normal polynomial over fq if and only if linearized polynomial of alpha is non-zero, where linearized polynomial is defined as coefficient will be the same summation tiv, the variables will be x raised to power q raised to power p. The next two propositions, they are also we will also use it in next section. Let f of x be a normal polynomial and g of x is equals to f of x minus a upon b. Then the polynomial gx is a normal polynomial if and only if na minus b c minus 1 upon c cn is non-zero, or we can say na plus b trace of an element alpha is non-zero. This is the main section. Here we prove that this transformation x raised to power p, this transformation can also be used to construct a sequence of irreducible polynomial and then further for normal polynomial. Lemma 3.1 states that if we have a polynomial f of x, which is irreducible polynomial of degree n, then f of x, we write f of x as x raised to power p raised to power n f of x raised to power p minus x raised to power p minus 1 plus 1 upon x raised to power p, then we prove that this polynomial is irreducible polynomial if and only if trace of n plus f star dash of 0 upon f star of 0 is non-zero. F star is nothing but reciprocal polynomial, and dash denotes the derivative of this polynomial at point 0. Here is the proof of this theorem. We'll take an element alpha, which is a root of f of x. Then using the proposition, this polynomial f of x will be irreducible if and only if x is to the function in numerator minus alpha of the function in denominator is irreducible over fqn. In particular, after simplification, f of x is irreducible if and only if x raised to power p minus x raised to power x raised to power p minus x minus alpha minus 1 is irreducible over fqn. Then again, using proposition 2.4, we'll prove that this polynomial is irreducible if and only if trace of the element alpha minus 1 is non-zero. Now we'll find the value of this, we'll find the value of trace of alpha minus 1. We have alpha is a root of f of x. This implies that alpha minus 1 is a root of fx plus 1. Then we can write trace of qn by p of alpha minus 1 as trace of q by p into trace of qn by q of alpha minus 1. Then trace of alpha minus 1 is n plus cn minus 1 upon cn. And using these two equations, we have trace of qn by p alpha minus 1 is equals to trace of n plus cn minus 1 upon cn. Therefore, the polynomial f of x is irreducible if we have this condition, trace of n plus f star dash 0 upon f star d 0 is non-zero. This proves the lemma. The next theorem is if we have a polynomial f of x which is irreducible and satisfying this condition, then we define f for x for r greater than equals to 1, x raised to power p n p raised to power r minus 1, f r minus 1 of x raised to power p minus x raised to power p minus 1 plus 1 upon x raised to power p. Then we'll prove that these polynomials are irreducible polynomials having degree NPR. To prove this, we use the above lemma and we'll prove this theorem by method of induction. F1x is irreducible over fq if and only if trace of n plus f star dash 0 upon f star 0 is non-zero by using above lemma. Then similarly, f2x will be irreducible if it satisfies this condition. For this, we have to calculate f1 star dash 0 and f1 star at point 0. We'll write f1x from the statement. F1x is equals to this polynomial, and then we'll find the reciprocal of this polynomial, which is f1 star x, which will be summation ci x is to the p minus x plus 1 raised to power I. Then at 0, the value of f1 star x is f of 1. Similarly, we will find f1 star dash of 0 at point 0, which is minus f dash of 1. Then this will be equal to trace of f dash 1 upon f of 1. Therefore, the polynomial f2x is irreducible if and only if trace of f dash 1 upon f of 1 is non-zero. This concludes that f1x and f2x are irreducible over fq. Now we prove it for some number m, that mx is irreducible over f, where m is less than or equal to r minus 1. We consider that these are normal polynomials, and we will prove it for frx. Now, using the above lemma, frx will be irreducible if and only if trace of fr minus 1 star dash of 0 upon fr minus 1 star of 0 is non-zero. For this, we will find this and this polynomial, and we'll get the value of f star r minus 1 0 is f of 1 as earlier, and the value of f star r minus 1 f star dash r minus 1 at 0 is f dash minus 1 minus p raised to power r minus 2 f dash 1. So we get trace of f star dash r minus 1 at 0 upon f star r minus 1 0 is equals to 1 minus p minus of 1 minus p of r minus 2 trace of f dash 1 upon f of 1. So we have that the polynomial frx is irreducible if and only if we have this condition, which is already given in the statement. This proves the result. Further, these further, the next lemma is for to prove the polynomial which we have defined earlier is normal polynomial if and only if this condition satisfy. For this, if we have a polynomial f of x, which in the statement we have f of x is a normal polynomial. Since this is irreducible polynomial and using lemma 3.1, this will f of x will also be normal polynomial. Let alpha be a root of f of x. Since this is normal polynomial, therefore n plus, which is already given in the statement, n plus f star dash of 0 upon f star 0 is non-zero, which is nothing but cn minus 1 upon cn. Therefore, using proposition 2.6, the polynomial f of minus x plus 1 is a normal polynomial. Now, to prove the polynomial f of x is a normal polynomial, we simply prove that the linearized polynomial of any of root of f of x is non-zero. The factorization of x raised to power p minus 1, we can write it as verify x in the product of these elements, which are distinct irreducible factors of x raised to power n1 minus 1. We write hix as this polynomial. Then we take alpha 1 as a root of f of x. Then beta 1, which is equals to 1 by alpha 1, is a root of f star x. Here alpha 1 is a root of f of x. Then we will prove that linearized polynomial alpha 1 is non-zero. Then using the proposition fx will be the normal polynomial. Now f star x is equals to x raised to power pn f of 1 by x, which is reciprocal polynomial f of x. Since alpha is the root of f of x, also beta 1 p minus beta 1 plus 1 using this equation is the root of f of x. Then after simplification, we'll get linearized polynomial of alpha 1 is equals to linearized polynomial of 1 by 1 minus alpha. Since this is the root of normal polynomial, therefore for sure its linearized polynomial is non-zero. Since this is non-zero, therefore linearized polynomial at alpha 1 is also non-zero. Therefore we have f of x is a normal polynomial. Next, for a normal polynomial f of x with f minus x plus 1 is a self-reciprocal polynomial, we'll prove that this sequence is a sequence of normal polynomials of degree n p raised to power r. Again, we will prove this theorem by method of induction. Since f1x is normal, we consider that fr minus 1 for r greater than equals to 2 is normal polynomial, and we'll prove that frx is a normal polynomial. For this, we take root beta r minus 1 of fr minus 1 of x, which since this is a normal polynomial, therefore beta r minus 1 is a normal element. And using the previous lemma, linearized polynomial of 1 upon 1 minus beta r minus 1 is equal to linearized polynomial of alpha r. Since 1 minus beta r minus 1 is a normal element, because f r minus 1 is a normal polynomial, therefore 1 upon 1 minus beta r minus 1 is also a normal element, because this is a self-reciprocal polynomial. So this is normal polynomial. Therefore, linearized polynomial of this element will be non-zero, and using this equation we have linearized polynomial of alpha r is non-zero. Therefore, we have frx is the normal polynomial. This is the conclusion. For a suitably chosen initial irreducible polynomial, we constructed the sequence of irreducible polynomial using this transformation, and later on we find that these polynomials are also normal polynomials of degree n p raised to power r. These are some references. Thank you. Thank you for your attention.
Thank you, Ashima, for that wonderful talk. Are there any in-house questions from the offline audience?